Welcome you all for this structural analysis course. So today we'll discuss about analysis of continuous beams with sinking of support by using moment distribution method of analysis. So this is week 6, lecture 1, CDT16. Myself, Rajshekar, Assistant Professor at Department of Civil Engineering, Bharatiya Institute of Technology and Science, Varanasi. So right. So these are the two lecture outcomes. After completion of this lecture, student will be able to calculate the fixed moments, the distribution factors, the continuous beam, and they can able to analyze continuous beams by using moment distribution method of analysis. These are the two lecture outcomes. Right. So first we'll see how the sinking effect on the sinking of support will affect on the fixed moment. Okay. Continuous beam we'll see. So if you consider the continuous beam A, B, C, so this is a continuous beam. Let us say I will draw here. This is a continuous beam A and B, C. So this is B and it is C. Let us say if intermediate support is settled by delta. So intermediate support sinks by delta. Intermediate support is sinks by delta. Then the fixed because of the settlement of this intermediate support, there will be some fixed moment that is going to develop in the two other supports. So let us say this is A and this is B and this is C. If support B sinks by delta, the support B sinks by delta downward direction, there will be some moment will going to develop at A as well as B only because of the settlement of support B. So along with the loading. So fixed moment will going to develop due to loading, due to settlement of support, and due to sinking of support and rotation of support. So because of this settlement of support, the moment developed at other fixed rates for ends A and C, there will be 6EI delta by L square, 6EI delta by L square. So for this, a derivation will be there. That you need to, I'm going to provide the course material. So in that, I'll give you this derivation 6EI delta by L square. And this is also here, we're going to develop 6EI delta by L square. So if this is a respective left side support, the right side support settled by delta, then the produced moment will be developed moment at the both ends, that is MFAB as well as MFBA, both are in the anti-clockwise direction. Anti-clockwise direction, that is negative W 6EI delta by L square. 6EI delta by L square. But in case of with respect to right side support, if left side support settled by delta, then the magnitude is same. Fixed moment magnitude is same, but the difference is direction is different. That is 6EI delta by L square. Okay. Now we'll see the problem related to this continuous beam with sinking of support. Analyze the continuous beam as shown in figure by moment distribution method. If support B sinks by 9 mm, take EI is equal to 1 into 10 to the power of 12 Newton meter square mm square throughout. Draw the bending moment diagram. So this is the given problem. You see, this is a two-span continuous beam, and so another span is there, that is overhanging is there, that is overhanging CD of intensity 20 kN. Okay, intensity, a point load of 20 kN is active, that you have to observe carefully. And B and C are the roller supports, and A is a fixed support. AB span is subjected to 60 kN load, and BC span is subjected to 20 kN per meter. Okay. For CD, overhanging support is there. So for CD, hanging load, that is overhanging load is 20 kN active. The distance from the support to critical load is 1 meter. Okay. So before going to the problem, first step what we need to do, we have to calculate. I'll write the step by step procedure here. First step, you have to calculate fixed moments. Second step, you have to calculate the distribution factors. Third step, you need to calculate the, you need to draw the distribution table. From this distribution table, we can able to calculate the final movement. So from these final movements, you can able to draw the bending moment diagram. Okay. First, we will see how to calculate fixed movement. So we know here AB span is subjected to eccentric point load. For eccentric point load, the bending moment, the fixed moment formula is minus WAB square by L square. So this is the well-known formula to you. You have already learned this formula from this past 2 units. Past unit also you have learned this, as well as we are using this same formula for the second unit also. Okay, so that is minus WAB square by L square. So that is, we calculate, substitute W is equal to 60, A is equal to 2, and B is equal to 1 meter. L value 3 meters. We substitute it, you're going to get AB is equal to minus 19.33 kN meter. Similarly, MFBA will be, substitute MFBA is equal to plus W A square B by L square. A square B by L square. So this is the formula. And also, so this will be the positive side. For AB span, MFBA will be, MFBA will be, MFBA will be, so because of loading, 2 meter and it is 1 meter, because of loading, this is the formula, plus WA square B by L square. But the given problem is also mentioned support B settled by delta. Because of the settlement of support, there will be some fixed moment we going to develop. So how to calculate the fixed moment? CI delta by L square. Okay. With respect to left side support, right side support settled by delta of the only. So the moment will be anti-clockwise. The moment will be anti-clockwise movement. Movement developed at A and B or both are the anti-clockwise. Okay. So here you need to substitute CI delta by L square. So minus WA square by L square minus 6 EI value given in the problem. Delta value given 9 mm. So we need to convert into meters. L value is 3 meters. So if you solve this one, you're going to get AB is equal to. So including effect of sinking of support, of support, to calculate. So this will be final fixed moment. So fixed moment by considering load as well as the sinking of support. So this is the value. That's 19.33 kN. Similarly, MFBA is also, MFBA is equal to same effect. So negative effect will be there, but we go there A as well as B. So if you consider MFAB as well as MFBA, so this moment, the fixed moment will be minus 68 delta by L square. So minus value have to be here. This WAB square by L square minus 68 delta by L square. So here also minus 6 EI delta by L square. Here also minus 68 delta by L square. So you need to substitute, you will go into this one. So coming to BC span. So BC span, for the BC span, with respect to right side support, left side support is settled by delta. Respect to right side support, left side support is settling by delta. Because of this, here we will get clockwise effect. Movement will be clockwise movement will going to develop. So clockwise means, so here for BC span, uniform distributed load is, so uniform distributed load came to minus WL square by 2L for left side support due to loading minus value we will get minus WL square by 2L. We know very well about this. And for settlement of support, here clockwise movement will going to develop, that is plus 68 delta by L square. Okay. So if you substitute these values, you will get minus 58.5. So similarly for this, plus WL square by 12, so uniform distributed load, plus XCI delta by L square. So this formula will be used for the calculation of fixed moment at a CD. Okay, similarly, for overhang, the moment of 20 into 1. So moment acting at C will be 20 into 1, that is 20 kilonewton meter is acting in the clockwise direction. But here resisting moment will be minus 20 kilonewton meter. That we have to, that is the end moment is will be considered as a fixed end moment. Minus 20 kilonewton meter will be considered to be fixed moment for the CD member. The CD member fixed moment will be minus 20 kilonewton meter. So after calculation of these fixed moments, we have to calculate the distribution factors. Okay, we need to calculate the distribution factors, right? So for the calculation of distribution factors, first of all, we need to identify how many. We need to draw this table. So we have 5 columns in this table. You need to remember this column: joint, member, stiffness or stiffness factor, or joint stiffness, and distribution factor. So distribution can be calculated by member stiffness by joint stiffness. Member stiffness by joint stiffness. So K will be the member stiffness by joint stiffness. That is your distribution factor. Okay. So now coming to the joint B. You see the joint B. At joint B, 2 members are meeting. First of all, I'll draw the figure here. In fact, it is a roller support. Uniform distributed load. This is also roller one. And the overhanging is there. Okay. So 20 kilometers acting. Okay. 60 kilometer, 20 kilometer. This is 60 and it is 20 kilometer. This is support A and it is B and it is C. Now we'll see. At joint B, 2 members are meeting, BA as well as BC. That we need to write here. BA. At joint C, CB as well as CB. So CB as well as CB. This is CB actually. CB as well as CB. So after that, we have to calculate the member stiffness, that is K. How to calculate K if the far end is fixed? Formula is 4EI by L. Far end is fixed. Formula is 4EI by. Okay. So L value we know this is a 3 meters. Given the problem, this is 2 and this is 1. Okay. So this is 6 meters. This is 1 meter. Given the problem. Okay. Right. Coming to the for BC member. So for BC member, far end is hinged. Far end is hinged. So this is not intermediate support. This is far end. End support. End support. End support is a roller support. For end support, roller support, we have to consider the formula is 3EI by L. 3EI. Stiffness will be going to reduce. That is 3EI by. Okay, 3EI by L. So L value is 6. So stiffness, member stiffness will be for fixed and fixed support, AB support. Member stiffness is 1.33. For BC for BC number 0.5. Yeah. So coming to joint C, at joint C, CB as well as CD members are there. So for CD member, for it is not a foreign, it is a intermediate support. So it's they also considered to be fixed support. Then the formula we can use that is 4EI by L for the calculation of stiffness. 4EI by L, 4EI by L. Okay, for CD, that is free end, that is stiffness will be 0. For this free support, stiffness will be 0. That means it will not take any movement. It will not resist any movement. So the stiffness of that particular member, CD member, is 0. Okay. Now you can calculate joint stiffness. So how to calculate joint stiffness? Just add these two values. So member stiffness, if you add summation of all the member stiffness at the joint, that will be a joint stiffness. The joint stiffness you have calculated for the both the joints, as well as the distribution factor will be equal to member stiffness by joint stiffness. You are going to get the distribution factor for the member BA. So similarly, member stiffness by joint stiffness, you are going to get the distribution factor for the joint BC. So like that, you are going to calculate the distribution factor. So after calculation of distribution factors, we need to form the distribution table. So this is a distribution table. First of all, you need to write the supports A, B, C, D, A, B, C, D. Those are the supports you have to write. After that, in the first step, you need to calculate. You need to write the distribution factors DF. So distribution factor at A will be 0. That is 1. Let us say this is 1. At D it is 0. At C, at B, BA member is 0.727. That we are calculating. Just now we are calculating that we need to write. And for BC 0.273, CB 1, CD 0. After that, we are write the fixed end moments. So those that we are already calculated in the first step, whatever we have calculated in the first step, so these are the fixed moments that you have to write here. 19.33, 20.67. So all like that, you need to write the fixed moments. So now coming to the this. Here we have some unbalanced moment is there. If you see the CD member, you see the CD member, it joint CD. At CD minus 20 kilonewton is there. At CB 61.5 kilonewton is there. So there is some unbalanced moment is there. So we need to calculate the axis unbalanced moment. So unbalanced moment is plus 41.5 plus 41.5 moment is there, that we need to balance it. We need to balance it. So plus 41.5 kilonewton meter unbalanced moment is there. So to balancing this, so we need to add minus 41.5 kilonewton meter at the joint C. At the joint C, we have to apply minus 41.5 kilonewton meter at the joint C. This much amount of moment we need to apply at the joint C. So because of this application of moment at the joint C, by allowing rotation at this joint C, if you apply the 41.5 kilonewton minus 41.5 kilonewton meter moment, so there will be some moment will going to develop at the far end. If the far end is fixed, some of the moment will going to develop at the far end. That is, half of the moment will develop at the far end also. So the developed moment will be parallel. So this will be carry over. So this moment will be called as carry over. Okay. Now you can observe. Now you add these both, and you add it, you will get 20.67 here. So here you will get minus 58.5 minus 20.75. Now what you have to do, you need to do this one. Calculate the unbalanced moment. Calculate the unbalanced moment at B and multiply with 0.727. We have 0.727, and you need to write here. Yeah, again you calculate the unbalanced moment and multiply with 0.273. You need to write. Okay, we are whatever the unbalanced moment is there at joint B, we are distributing to member BA as well as member BC. So how we are distributing based on its distribution factor, we are distributing. We are calculating unbalanced. How do we calculate unbalanced moment? We are carry forward some moment from C member to the B member. So you have to add a resultant moment here. And, you need to add resultant moment for the BC, resultant moment for the BA. You need to subtract BA moment minus BC moment. So you're going to get the unbalanced moment value. So let us say here unbalanced moment. So 58.5 plus 20.75 minus 20.67, around 50.58 you're going to get, around 58, 58.4 you're going to get, minus 58.4 amount of unbalanced movement is there. So to balance this, we have to add this 58.4 kilonewton meter. That is joint. Because of the application of 58.4 kilonewton, so some of the movement carry to the BA member, some of the movement will carry to the BC member. Okay. So how it will carry it is based on its distribution pattern. So 58.4 multiplied with 0.727, we need to write this value here. 58.4 to 0.273, we need to write here. Okay. So after that, so half of the movement will carry to the foreign. Half of the I can carry over theorem, half of the movement will carry to the foreign. So now you add all these movements, add all these movements, add all these movements, you're going to get the final end movement. So here the joint equilibrium equation is satisfied. So these are the final end movements.